Good afternoon, everyone. Am I audible?
Yes, sir.
So let us wait for like 1-2 minutes. So if anybody else wants to join, so we can wait for 1-2 minutes. And let us start from 3:05. Today's problem solving session. Whose email ID? You want my email ID? So my email ID is so I'm sharing my email ID. No worries. So this is my Gmail ID that I have shared right now with you. So still some people are joining. Let us wait for 1 minute, one more minute, and then we can start today's session. So I think let us start with today's session. Um, Good afternoon, everyone. Am I audible? Just to reiterate or confirm, can anyone please reply? Okay. Uh, so my screen is also visible. Anyone can reply in the chat. Screen is visible to everyone. Okay. So good afternoon, everyone. I am Adnan Farooq Khan. Uh, today, this is the week third of our problem solving session for the course Design of Power Electronic Converters that is being taught by Professor Shabrinath. And as you already know, I am a research scholar from IIT Delhi, and I am doing this problem solving session on every Sunday from 3 to 5. So as I told you, like this is our third week problem solving session. Like every problem solving session, briefly I'll be going through what has been taught in this week. Then we shall be moving some of the problems that will be solved, and just to help you with your assignments, and may some similar questions may come in your exams, so that that should help you uh, in solving those problems. So coming to this week, like everyone knows what we saw in the previous week is that we saw about like diodes, different types of diodes, their characteristics, the data sheets of some diodes, what has been how to like see different parameters in the data sheet. And after the diodes, we move towards the MOSFETs. We saw their switching characteristics, some of the parameters that are given in the data sheet, what are the important parameters that we have to look for these devices. In order to like choose a particular device for uh, for a design parameter, if you have in any converter, how to choose these parameters. Like continuing with that, like what had been taught, another important uh, device that had been taught in this week, continuing with the previous, is an IGBT. So we'll be seeing the characteristics of IGBT, some data sheets, some of the terms affiliated with the IGBTs. Then after this IGBTs, an important topic was like discussed is like gate drivers. Like if now we know we have these devices like IGBTs, MOSFETs, how to drive these devices, how to turn and turn off these devices, what are the different requirements in order to turn on these devices, and so on and so forth, so this has been discussed in detail. We'll be briefly going through what had been discussed during this week, and subsequently after that we'll be discussing one of the gate drivers, like that are opto coupler based gate drivers that we'll be discussing, and what had been taught, what are its different what are its like different features, its requirements, and so on. So the first thing like we come to the IGBTs. Last time we had seen is a MOSFET. So similar to the MOSFET, like we have an IGBT. You can see IGBT. This is the symbol of an IGBT. Like in the MOSFET, we had a drain, source, and a gate, and here what we have is a collector, emitter, and a gate. This is an NPN MOSFET, and we know that um, this IGBT compared to the MOSFET, like this IGBT is a unidirectional device. It is able to conduct the current in only one direction, that is from the collector to emitter, in this fashion. And also this IGBT is able to block the voltage in one direction. It will be able to block a voltage until like we'll give uh, this gate voltage and turn on the device. Till then it will be able to block that voltage, and as soon as we'll give this gate emitter voltage, our device will go on from the cutoff to the active region that we'll see subsequently in the characteristics. And compared to this MOSFET, this IGBT, as we know, is unidirectional. And what we had seen in the MOSFET, that MOSFET was able to conduct the current in both directions through its drain source channel. So it could conduct a positive as well as a negative current. Also, we had a body diode across this MOSFET, which was able to like conduct the current in the negative direction as well. So in order to have this bidirectional current carrying capability in the IGBT, so what is being done for the different IGBTs is like we have a anti-parallel diode across this collector emitter terminal. So we have an anti-parallel diode here across the collector emitter, so that there will be a path when the current will be in the opposite direction, so it shall flow across along that diode that is connected between the collector and emitter. Also, other difference from this MOSFET is that this IGBT, like you would have seen through this week that has been taught in detail, is like that this IGBT is a minority carrier device, and we saw like that this MOSFET was a majority carrier device, but this IGBT is a minority carrier devices. And as such, like because of this minority carrier, the large number of charges that are available in this IGBT, is what we have is we have, compared to the MOSFET, we have a low on state drop in an IGBT compared to the, because of being a minority carrier device, this on state drop in an IGBT is low compared to the MOSFETs. So the advantage of this low on state drop compared to the MOSFET is like you can understand in a way, like for a particular device, if we have a low on state voltage drop, we can go to higher voltage ratings for particular for a particular device compared to the MOSFETs, because now we having, for that higher voltages, we'll be having a lower drop compared to those MOSFETs. As such, you can see these MOSFETs will be rated for higher voltage levels compared to the MOSFETs like will be having around like 600 900 volt MOSFETs, but you can see the IGBTs that are of the higher ordering, like 1200 like 1.7 kV 1200 volt 1.7 kV IGBTs will see as well. But being the minority carrier devices, what is there, like during the turn on and turn off process, like there will be some tailing current towards the end of that we will subsequently see in the switching characteristics. And you would have been taught in detail during this week that because of that what we have there, this IGBTs will be having the slower switching speeds compared to that MOSFETs. So where these IGBTs lie, they lie in terms of the switching speed between the BJT and the MOSFET. Like these are having the lower switching frequencies than the MOSFET, but are able to handle the higher voltage levels compared to the MOSFETs. So besides this, what is this is like the other aspect of this IGBTs are, these are voltage control devices. That means whenever this gate to emitter voltage is given, like it is beyond the threshold voltage, then this goes into the conduction mode. So these are like some of the like features of this IGBT. What we saw is it is a unidirectional IGBT, and it itself is a unidirectional device until we have an anti-parallel diode connected across the collector emitter that will carry the direction that will carry the current in the in the other direction, making it as a bidirectional device. Then also IGBT is like able to handle the voltage in only one direction. Moreover, like other feature is like it's a minority carrier device. It has a low on state drop. Because of that, their voltage ratings of these devices will be higher. And this would be, being the minority carrier, we have a tailing current, and they takes to more time to turn off, and because of that we cannot like switch these IGBTs at higher frequencies compared to the MOSFETs. If we see, besides this, other feature is like it's a voltage control device. Now coming to this characteristics of VI characteristics of the IGBTs, like we had seen in the MOSFET in the uh, previous week, we had seen the VI characteristics of the MOSFET. In a similar fashion, we have the output characteristics of these IGBTs. I won't go into the much detail because like this has been discussed in the previous week as well. So I'll be briefly going through this. Like the VI characteristics of this MOSFET is like we have three main regions. We have a forward blocking region, active region. This is also called as the cutoff region. Then we go into the active region. Then we have a saturation region. And here we had seen in the MOSFET is an ohmic region. So what happens as soon as we give if the gate source voltage is below the threshold, or it's like 0 or negative, what we have our like IGBT in the blocking mode, that it is able to block the whatever voltage that will come across to it. Of course it will be able to handle the voltage to it is rated, and it cannot handle the voltage beyond that. Let us say we have an IGBT that is rated to, let us say, 1200 volts, so it will be able to handle the voltage up to 1200 volts, not beyond that. And if we apply the voltage beyond that, that may damage the devices. But as soon as we will give the gate voltage across the VGE terminal, now beyond the threshold voltage, now our device will go in from the forward blocking into the active region. You can see in the active region we will be having a constant current will the device will go into the conduction, but we'll have a constant current flow that will flow through this drain to, so from collector to emitter, collector current. But as soon as we will be increasing the VGE will be increasing beyond the threshold volt, will subsequently move from the active region to the saturation region, where we want our devices to operate, because like we want to have a uh, linear sort of VI characteristics. Also you can see in the saturation region our device is able to handle very high amount of the current, and these current will only be like the current will be determined by the output circuitry to these IGBTs. So these are like the switches, and how to limit these current, this will the amount of current that will flow through this will be limited by the external circuitry. And also you can see in this saturation region we are having a very small drop compared to this, so the power losses will be less in the saturation region compared to the active region, where we'll have a high VC as well as IC. And these were the three: forward blocking, active region, and the saturation. Also, what is different from the MOSFET characteristics is like we have a constant some drop initially, similar to in fashion of a diode. After that it will start conducting. Here in the MOSFET we had an RDS that was causing a drop of like IRMS into RDS on. That is one thing that is different from the MOSFETs. And after that, similar to this, we had seen the transfer characteristics in the MOSFETs. These are similar here, like if you can see, when we apply these are for transfer characteristic is the graph between VGA and IC, collector current, and VGE voltage. So if you see, when our VGE voltage is 0, our device is in turned off, like it is in the cut-off mode or a forward blocking mode. But as soon as we are increasing the VGE beyond up till the threshold voltage, there is no current that is flowing, but beyond the threshold there is some current that will flow. But if we keep on increasing the VE, it will move from the forward blocking them to active, then to the saturation region where we have a linear, where we have, and if we have a slope of like IC and VG graph, like that is known as like a GFE. Like this shows us the transfer characteristics that had been previously discussed in detail in the MOSFET characteristics. These are similar to that thing that I shall not be going into the detail here. So this was about the VI characteristics. Then we have to see about the switching characteristics. So before going to that, like I want to reiterate like how these we are like characterizing these switches, how we are able to have if we want to measure, if we want to test any devices for like we have to measure the switching characteristics, different characteristics of the switch. What we do is we do a double pulse test. So what is this what we do, why we do this double pulse test is we want to test a particular device, how it behaves, like what is it's the rise time of the current, how it behaves. Like if you have a device that is rated from for some voltage and for some current, we put that device under the test and see what are like the turn on and turn off losses uh, of these devices at the turn on time as well as the turn off time, how these devices will behave. So if you want to characterize devices and what we do is we do this double pulse test. And when you see in the data sheet different parameters that are put for a particular devices, like that devices have been gone through a number of tests. This is one of the tests that a device goes through when we characterize any devices. So the if you can see here, the device setup here is like we have a two devices, like an H bridge here, we have a top devices as and a bottom device. And if you can see, we have an inductor that is connected across the top device, and usually, and we have a bottom device, and we have a DC link that is connected across this H bridge. So the here what is being done is the top devices, what we keep is we keep these top devices in the off state. So what we can do is we can connect this, we have like C, E and G, we can connect like G terminal to E, or we can have a gate driver that will give a negative voltage here, and we can have this device in the off state. And this devices is bottom devices, this is being turned on and off. And usually we like apply the two pulses to it, like we turn it on twice. That is why we call it a double pulse test. And usually this bottom device, what we call it a device under test, that is DUT. If you see any of the document application note, you can see that it is being written DUT, that is device under test. So this is the device under test, and we apply this VDC voltage. If you want to like test this device for a certain amount of voltage, that is the voltage that we apply here in the VDC. And our devices that we know that our device will be like will be designed for a particular voltage as well as the current rating. And if we want to like now test this device at that current rating, so what we do is now we have this we have this sort of a setup. So now if you can see, when the top device is on and bottom device we give a pulse, you can see here when this like this top device is, when this bottom device is turned on here, if you can see here, when we give it the first pulse, you can see this VDC voltage will come across this inductor, and the current, we know that the current that will flow through is equal to LDI by dt. We can with this L, like we can control the slope of this current. And now if our device, let us say, is rated for some amount of current, let us say 50 amps, or 100 amps or whatever, 60, 70, any amount of the amps. So by controlling this width of this pulse, because like we know we have the control, we know the L value, we have the L d is equal to di by dt. If we are able to control the width of this pulse, when as soon as we will give the pulse here, the current will start to rise across this linearly and it will reach some point. And usually we go to the current peak rating where we want to test this device. Let us say we want to test this device as a 50 amps. So what we do is this peak current will be equal to 50 amps, and at that time, at that moment, we will turn off this device. As this device is being turned off, what will happen? We know that we cannot interrupt the current instantaneously. We cannot interrupt the current flowing through the inductor. So what will happen? This current will freewheel through the top device's diode here. It will freewheel. It will freewheel here. Usually what we see is like what we assume is like there is no change in the current flowing. So if you can see, our current has risen, let us say for example from 0 to 50 amps, and after some time, at that moment our bottom device is turned off. So this current will now freewheel in this loop, and only like the voltage that will be across this is the voltage drop of this diode, and there won't be a much of an appreciable change in the current. So we can assume that more or less this IL will remain constant. So at this point what we are doing is we are turning off this device at some rated current, let us say 50, 60, 70, any amperes of the current. So here we are able to capture the turn off of the device. So we will see how our device behaves at the time of the turn off. We can take the different waveforms like voltage current waveforms at the turn off interval. Then we can see how our current like di by dt of the current, and so on and so forth, other things by which we will be able to measure like the turn off losses and etc. So this is how we characterize here. This instant will give us the turn off characteristics. After some time, like we then again give a pulse to this, and what happens is, because we are assuming that this current is same, so our device will turn on at the same current, and what will happen, this will give us the turn on characteristics at this amount of the current on this current at the similar current rating. And after time we give this pulse to some current rating, so that our current should not go to that may device that may damage our system, that may damage our this device. So we give it a short pulse this second, and after that we turn this off. So what happens is like to measure, if you can like summarize this thing, to do the switching characteristics, we do the double pulse test of this, where we have an edge bridge where the top device is in the off state, and we have an inductor across it, and the device under the test, we give the two pulses across it. That's why the double pulse test. So what we saw is during the first pulse, what happens is the current builds up from some zero value to some rated value where we want to test our devices. And at the end of this first pulse, when we turn off, what we can get is the turn off characteristics of this device. And as soon as we give the pulse, second plus pulse, at the start of that pulse, what we will get is the turn on characteristics of this device. And in this manner we are like able to characterize this device for turn on and turn off. We can calculate the losses and etc. things. So this was about the characterization, how we characterize the devices. That has been the data that has been provided, how the data that is being given in this data sheets, how we come up with that data. So we do these different tests and try to like calculate as accurately possible what are the like characteristic of a particular device. So after that, like what we'll be seeing is like the switching characteristics of an IGBT. And as you can see, like this is the in a similar fashion like we had seen how this IGBT, how this MOSFET was turned on switching characteristic of a MOSFET we saw in detail in the previous week. In a similar fashion, like we have the switching characteristics of an IGBT. You can see before like our devices is before I like rush through this, because like this has been discussed in detail in the previous week. So I'll go through this in before this device is turned on, we have a negative voltage that has been applied to the devices, and as soon as like we want to like turn on this device, so what we apply in so here this is of the MOSFET. So in IGBT what we apply is we apply VGE voltage, like this is here VGE voltage. As soon as we apply this VGE voltage, so the voltage may build from some negative voltage or a zero voltage to some voltage first threshold. So we call this as turn on delay time up till this point. And after that, as soon as there will be a no conduction, because our device will be in the cutoff mode up till the threshold. As soon as our gate voltage crosses the threshold voltage, what we see is the drain current will start to flow. And that is a similar way we had seen in the MOSFET, and it will go to some peak value, and this current it can overshoot, and after that it comes down, and our gate voltage then reaches to the Miller voltage that we had seen. So someone is having a doubt. Galia, you can write the question. What is the doubt you are having? So it reaches to the Miller, and after that,
Hello, sir.
yeah, you can ask a
I
question.
have a doubt that why always the current first increases, rises, then the voltage drops.
Okay, so what happens is actually like as soon as what this if you can see, we'll come after that, this the switching characteristics here, what happens, how this switching is. When we see the gate drivers, we'll see in the detail in the subsequent states slides. How it happens is like when this voltage is what happens is like the device tries to go into the conduction mode, the current starts to flow through this ID. So what will happen, that when the current starts to flow, after that what happens, before that some voltage is being blocked across the device. As soon as the current will start to flow, first the current will stop, because when we apply the gate, if you go into the physics, and there will be some channel that is formed in the IGBT, and the current will start to flow, and after that VDS will start to drop. And when the current reaches to some value, then after that VDS across will start to drop, and it will go into the proper conduction mode. That happens during this Miller plateau, that our voltage will drop, that we had seen in the MOSFET. I hope like you were present in this previous it drops in the Miller. So our device goes into the conduction, and after that like our device goes some gate voltage further increases to the nominal voltage, and then there it is constant, and our device goes into the conduction in a similar fashion. Similar to this, we had an off state, like the MOSFETs first, like the VG voltage will go to some value, and after that Miller plateau, in that time that our output voltage will start to build up. If you want to like see in the detail, you can go to this MOSFET characteristics that had been taught in the course. Go through the transcript, and if you still are not able to like understand it properly, like you can like are free to like mail, or next time we'll be having a course, we can discuss it in detail. So compared to the MOSFET, what is in the negative, we have some, after this current begins to decrease because of the minority charge carriers, we have to get rid of those minority charge characters. If you go into the physics of it, so there will be some trailing current here. This was not in the tail current during the turn off in the MOSFETs, because the MOSFET was a majority carrier device, and it is because it is due to the device physics, like the conduct the conducting carriers in this here are the minority carriers. So we'll be having to, at the time of the turn off, to like extract these minority carriers. There will be some tailing current here, which was not in this MOSFETs, and because of this tailing currents, like this limits, this can increase our turn off duration in the IGBTs, and which in turn like limits our switching frequencies, which I had talked about earlier. So that's one of the difference in the IGBTs. We have a tailing current because of the minority carriers at the turn off interval compared to the MOSFETs. So this was like being discussed in this about the turn on, rise time, and fall. This time has been discussed in the MOSFET in detail in the previous week. So now we shall come to some of the data sheet terms. Some of the data sheet terms here. Data sheet terms. So in the IGBTs, if you can see this is the IGBT data sheet of this IGBT part number this. So you shall be able to you are acquainted with these terms, like this has been discussed in the previous week as well, like what is the collector emitter voltage. This is the, like here it is given 1200 volt for this IGBT, like it is the maximum of the voltage that it can block. And some what is given here, like this is the voltage rating of the devices. Now we have a current rating of this device at different temperatures, like at 25 degree it can have a maximum current of like 85 degree, and at 100 degree we have at like 45 degrees. So this is like the this is the maximum it can connect. Then we have the nominal current, like that can flow through this device. Also we have seen in the previous time as well the pulsed current, like that was the more, that was like a peaky sort of a current that it can flow for a small duration of a time through our devices. It can be higher than the rated current rating of these devices. And similarly we can have we have then if we have a diode, anti-parallel diode attached in the package provided in the IGBT, their rating, current ratings for diode forward current ratings are also provided, and their voltage drop as well. Also what is given here is like a continuous gate to emitter voltage. What is the maximum gate to emitter voltage we can provide here in order to like turn on these devices. These are some of the terms that now you should be able to you should be like understand easily, because like we have been discussing it for past 2 weeks. So after that, like we have some other terms like collector to emitter breakdown voltage, that has been like it's around like 1200 volts. Then there is like a temperature coefficient of the breakdown. It varies like with the temperature. So if our temperature rises, like our there will be some variation in the breakdown voltage, and it will vary with the like 0.18 volts per degree centigrade. Also like what is the saturation voltage for this collector to emitter, like typical value is 1.7 volt, and this is the ratings where this device has been tested at these, like collector of current of 30 amps, VG of this, where we can see this. We have a gate threshold voltage that is being provided, like the 3 volts. After this voltage, like our uh, device will go into the conduction, like we are seeing, and below this voltage it will be in the cutoff or forward blocking voltage. Similar like other terms like collector emitter leakage current, diode voltage forward drop, gate to emitter leakage current, all the other terms that are that will be provided in the data sheet. So some other devices, some other things that are provided is like you can see like total charge, up to what is the total charge to turn on the devices. Gate to emitter charge, gate to collector charge, we had discussed in the previous week as well. So other thing that has been that will be like is provided in the IGBT datasheet is the turn on switching losses. Here you can see turn on on and off losses. What are the losses that are associated with a particular devices? Like I told you, like we put a device under the double pulse test, we see this thing. Just a minute, sorry. We calculate these turn on and turn off. We characterize the devices, calculate these turn on and turn off time. Here you can see we have this E on. This gives us the turn on switching losses. Here you can see, and we can also see the variation of these by these graphs. We can see the variation of these E on and E off with respect to the collector current. More the collector current, more will be the E on and E off losses. And you can see here E off loss is less than the E on loss. You can assume why this is like E off loss is less than E on. What we had seen is we had this reverse recovery. Last time we had seen we had a diode reverse recovery. When there is a let us say then there is a diode recovery for reverse recovery current for the top. Let us say we have an H bridge and we have a top device and a bottom device. Now what the top device is turned off and there will be a diode reverse recovery there. What where this current gets reflected is in the bottom during the turn on of these bottom devices. So because of that the losses because of this reverse recovery also, that will get reflected into the turn on of the bottom devices. Because of that, one of the reason is like this turn on loss is greater than this. The other thing, that is the other graph you can see, is this turn on turn off losses variation with respect to the RG. Usually what is being provided here, turn on and turn off, in this data sheet, if you can see in the table, these are at a certain conditions. Like this devices has been tested at the IC collector current of like 30 amps at this voltage. VGE is like 15 volts, RG is 10 ohm, and L that we saw is usually in that inductance. It is like the whole lumped inductance that we had seen in the double pulse test, and at the temperature of 25 degrees, and this was the losses. Usually, like if we have different test conditions, like these values may not hold true, and we have to like see from the graphs and see different graphs, and what are from that we can calculate the turn on and turn off losses for the different parameters. And if because of the like the other graph here, you can see is the variation of turn and turn off with RG. We know that if we like increase the RG, we like increase the turn on time because of the increase in the RG, and because of that, when it takes more time to turn on, then the losses will be more. Turn on losses will be more. So that is because like that is why like with the increase in RG, our turn on our losses increase. The other things that are given here is like TD, turn on, delay time, rise time, off time, fall time, like we had seen in the MOSFETs as well. These are similar here, like these we see. And what are the things that we need for our designing a particular converter or anything. We go through these we go through these things and see if a particular device is suitable for us or not. Now this was about the IGBTs and all. Now we come to the important topic, is how to drive these. What we had discussed is here, like if we have a device, usually it is in the off state when there is like a zero voltage, when there will be a zero or a negative voltage across this G terminal. Now we want to turn on this device. How to turn on these devices, and why do we need these gate drivers? So usually when we want to turn on these devices, we have a controller from where we generate these pulses from this converter. When we want to turn this controller can be an analog controller or a digital controller. In the digital, we can have a DSP or an FPGA from where we get the pulses, how we want to turn on and turn off these devices. And usually these driving pulses have usually an amplitude of like a 3.3 volt or 5 volts. And what we see is this voltages may not be sufficient to drive a device, like we had seen for a particular, like we needed a VG of around 15 volts or 30 volts or so and so forth. So these voltages may not be sufficient to drive these voltage into the saturation region. Maybe these voltages may be able to push them into the active region from the cut of the region, but we saw in the losses in the active region only a constant amount of the current can flow through it, but we want our device to operate in the saturation region. So these levels are not suitable for us to turn on these devices. One of the reason is this. Another reason is like the current level of this controller may not be sufficient enough, because these controllers usually cannot like have a can supply the current in terms in milliamps or microamps, but in order to turn on device we may sometimes need current in the amps. So these controllers may not be able to uh, provide us that amount of current and voltages, that level of current and voltages. Also, one thing is that if you can see this H bridge, here we have two devices. One is the top device and one is the bottom device. So we have what we call this is there. We have a DC bus connected across these two devices, and this we call this top device as a high side switch, and this is the low side switch. So because like this is connected to the positive DC bus, and you can see this is to the negative DC bus. And if you can see, whenever this terminal whenever this top device is on or off, whenever this top device is on, we know this voltage at point A will be equal to VDC, and when this is off, it will be equal to 0. So the voltage at this point will vary from 0 to VDC, and whenever we have to turn on this device, we usually have to provide this voltage with respect to GE. So here we have to give these voltages with respect to this floating point, floating voltage that is there at the A point. So our gate driver should be able to provide this VGE voltage for a particular voltage with respect to this floating point A, and this is usually with the top side devices. For the bottom side devices, this emitter is usually connected to the negative rail, and this voltage is usually a constant and it doesn't fluctuate. So our gate drive should be able to have should be able to drive this high side switch with this floating type voltage. So these are some of the why we need gate drivers for a particular to turn on a particular device. So as I had discussed, one of the reasons is to meet the voltage and current requirements of driving the switches that I had told you or discussed, is the amount of the level of the voltage that is being provided by these controllers may not be sufficient enough to turn on these devices. Also, the currents at the time of driving these gate drivers are very high in amps, but the controller may not be able to provide us the current in these levels. So we need to shift these voltages and currents, and for that in order to drive the devices, and for that purpose we may need the gate drivers. And this was the first point, and also that I told you we need the level shifting. Also I had discussed we had the floating point supply here at this A, and for this high side switch we need to provide this GE voltage with respect gate voltage with respect to this floating voltage, and our gate driver should be able to do that. Floating supply should have this thing, so that it can apply the turn on this device with respect to this floating voltage at point A. The other thing is our gate driver requirement is our gate driver should have an isolation. So why we should have an isolation here is, if you can see here, we have an this is the like high power circuitry from here to the like the device here, and we need some voltage like 15 volt plus 15 or minus 5 that is being provided by the gate driver in order to turn on this device. And this voltage this voltage is shifted, like I told you, our controller may provide a voltage from 0 to 3.3, but in order to drive the devices we may require the voltage of like 15 or minus 5 in order to drive this device into the saturation region. So what this gate driver does is this level shifts this voltage from this 3.3 to 15 and minus 5 in order to drive this device. Also about the current, I was telling you, in order to turn on this device we may need a sufficient amount of current to drive these devices. About the isolation is, let us say any fault happens at the power side. So if that fault gets reflected to the if we didn't have this isolation, that fault may have been reflected to the controller, and we know this is a power circuit and our controller may not be able to handle that amount of the current, so it may get damaged. So what we need is our gate driver should be able to provide the sufficient amount of the isolation in order to isolate the power side from the controller side, so that our controller side may not get damaged. The other thing is, like, our gate driver should be able to provide us with the high input impedance. Why the high input impedance? So as I already told you, our controller is not able to provide or have a sink of high current. Only the amount of current it will be able to handle is in terms of the milliamps and milli or microamps. And this is our power side. In order to drive this, our IG is very high. We may require it in terms of the amps. So if our gate driver wouldn't have had this very high input impedance, so this high current would flow through this controller as well, which can damage our DSPs and FPGAs. But if we have a very high input impedance here at the gate driver, which will limit our current through the controller, so that it may not get damaged. So another requirement of the gate driver is that it should have a very high input impedance. So now we shall see here how this gate is like turned on, how this if we want our switch to turn on, how is it turned on, what is the process of the gate driving. So if you can see here, let us consider here, before the turn on of this device, there is like a 0 voltage across this device has been turned off, so VGS is 0. So now we want to turn on this device. What will happen is, at this time we may apply some VG voltage, gate voltage, sufficient gate voltage, let us say 15 volts, in order to turn on this device. But as soon as we apply this VG voltage, some IG will flow. So our VG will come across this VGS CGS, so it will charge this CGS. So our VGS will start to rise, and it may that we had seen, it will first reach to the threshold. After threshold, it will reach to the Miller plateau. So initially, if you see here, we had VGS before turning on of this device. We had a VGS was 0. Now we applied a VG of, like, let us say 15 volt. So this whole VG will initially get applied across this RG, because like this the voltage across this GS is 0 initially. So a high amount of current will flow initially as soon as we apply the VG, because the whole VG will be applied across this resistance. So you will see IG will rise to the peak value initially, but after some time this CGS will get charged, will start to charge. So our current and the voltage will build up across this GS across the CGS, and that will limit our current. So our current IG current will start to drop till the Miller plateau, because at the Miller plateau, like, this voltage will be the constant, and current will start to flow after the threshold, and the drain current will start to flow. And now what will happen, current will rise, and after this threshold, at the after this Miller plateau, this voltage across the CGS won't change. And what will happen, this IG will now remain the constant, because this voltage is constant, this voltage is also constant, so IG will remain constant, and IG will now flow through the CGD, and it will cause the CGD to discharge, and CGD and CDS will cause to discharge, and we'll see this. Now the voltage will drop across the VDS, and now this IG will flow through the CGD and cause the CGD to discharge. And you will see here the IG will remain the constant in the during the Miller plateau, and after this the current will start to flow, and VDS will drop and will come to the zero. And after this Miller plateau, like we had discussed, our VGS will rise to this peak value, and our device will go into the active region and start conducting. So this was about the turn on process, and the terms are we had already discussed is turn on delay time. This will be the rise time during this time, and during this time, during the TFV, this is the fall time of this voltage, and it will drop from this to 90% of the VDS. So this was about the turn on. Now if we want to, like, these are some of the equations that we if you want to calculate the certain things, you can see. If you want to calculate what is the IG peak value that will flow through this through the gate driver, like this is the VG, this will be provided by the gate driver. If you want to know this IG peak that will flow this here, we saw that IG peak will flow at the time of the start, of when we apply this VG voltage. Let us say that initially, like, there was a zero voltage here. So what is the peak will be that VG off was 0, then this IG peak will be VG divided by RG, what we had put RG here. And if we want to, like, limit the current, we can appropriately choose this RG value in order to limit our current under a particular value. Now if we have sometimes we have a negative voltage during the turn off. Let us say if I had a negative of a -5 volt during the turn off, so IG peak will be, let us say, VG of a 15 volt minus 1 minus of 5, it will be 20 volts divided by some resistance. That will be the peak of the IG current that will flow. Similarly, like, we can calculate if you want to calculate the value of IG2 that has been depicted here, that is during the half of the rise time. So what we can see is what is the voltage that will be here across the VGS at that time, that we will subtract from the VG and divide that thing. If you see the half of it, it will be the half of VTH plus VGS plateau. That plateau is Miller plateau, we call it the VGS plateau, and that will be the voltage across this RG divided by RG. That will be give us IG2 at that time. Now if we want to calculate the IG at the time of the Miller plateau, like, it is similarly like VG minus VGS plateau divided by RG. So also this was about the IG. Now if you want to, like, calculate the rise time and fall time, we can do that. We know the equations. If you can see the rise time, we know the rise. This is the IG 2. We know the I is equal to CdV by dt. If we know the CISS, we know these parameters IG2 and same things, and by that things we will be able to calculate the rise time of the device. So these things, like, we get these things, we had seen the double pulse test, so we perform these tests and we get these parameters, and by that things we are able to, like, calculate, and from that this data is provided in the data sheet. In a similar fashion, using this in the plateau, we at this fall time we can calculate, because we know the VDS off at that time, we know the CRSS, and that is provided in the data sheet, and we know this current, we can calculate the Ti is equal to CdV by dt. So these are the different parameters if you want to calculate, and if you have these given, you can calculate these things. How to calculate this? These are the formulas. Maybe in some questions there will be some question asked regarding these things. So it is about the understanding what is the current at a particular time, what is the voltage there. You can calculate the rate of change and everything else at that time. The other thing here is, if you can see, is about the gate driving process is the loss. What is the loss associated with the turning on and turning off of this device? So the loss will we know that if we have some we know some RG current will flow, and we have RG in the circuitry, so the loss will be like Ig RMS square RG, and there will be some loss also as such, that will be P gate loss, that is due to the charge of this, and that is this P gate is given by Vg, Qg and Fs, and you know that the total gate charge is provided in the data sheet, and you can see that we have a we can calculate this Qg from the graphs as well for the different VDS values. And this gate charge power loss due to the gate charge and discharge is dependent on the frequency, because like we will be turning on and turning off device at a particular frequency, and at that particular frequency we will be charging and discharging these capacitors. And because this charge is associated with, for the charging of these capacitors, like from this to this, this is the charging of this CGS capacitor, and then this is the plateau, and then this portion is again the charging of the VGS capacitance. So, and it is depend upon the frequency, and if we have the more frequency, and there will be a more more losses associated with the charging, turning on and the turning off of the devices. So this was about the losses. Now the other thing is, like now we will see about one of the gate drivers that are that is being used in order to drive the devices, that is like the optocoupler based gate drivers. So as you can see by the name itself, is optocoupler, like it is like this is an optical isolation that is being provided from one side to the another. So what we have here is, we have the two diodes. One is, we have a light to a light emitting diodes here. As soon as we'll give the pulse here on the one of the side, what will happen is, like this will be an LED, and some light will emit from this diode, and what it will cause the other diode to turn on. But there is some optical isolation from one side to another. So the controller side and this side you may be usually connected to the device side, so we have an isolation provided between the two sides. That was the requirement that we had seen is needed, that is the needed for our gate driving. So this is about the optocoupler, is the optical isolation. Usually what we have is like two light emitting, we have having the light emitting diodes, and for that we'll be providing this control signal from one side, and that will turn on this LED as per our requirement, and which will in turn turn on this diode on the secondary side and provide the voltage on the secondary side. And we had seen for driving a particular set of devices, we may require different voltage and current levels. But this simply this optocoupler based circuitry may not be able to handle that level of voltages and currents. So also what we had seen in is the floating, we had to take into the consideration of the floating supply, requirement of the floating supply. For that, the floating point of the high side switch, so that should also be how to take into the account that thing in this optocoupler based gate driver. And I also seen said that what we require to turn on this particular device, we require the higher currents, and usually like these diodes, this optocoupler may not be able to have that current levels in order to drive a particular device. Now we'll see how we'll be able to, like, we'll look into these problems and how will we tackle these things. So one of the thing is like to provide a proper level of the voltage at the to drive this particular switch is we have a totem pole sort of a configuration. So what we have is here, we have a totem pole is like we have the two switches which are in where the top device is the NPN transistor and the bottom is a PNP transistor, which are base of the both of this is connected to the optocoupler output. And we have the PNP is connected to the VS positive, and NPN is connected to the VS positive and PNP to the VS negative. What happens is as soon as we give these control signals, it turns off this secondary side diode accordingly. What happens is as soon as this is turned on, it will drive the NPN transistor at that moment whenever the secondary side is turned on, and this PNP will be in the cutoff mode. So what will happen at that time, if this top device is turned on, this VS voltage will come across this VG gate, and usually this voltage is provided with respect to this source. So we will have this VS voltage, and here we can have this appropriate VS positive. Let us say we want a 15 volts, so this VS positive will be a 15 volts, and that will be with respect to this source. So as soon as this signal will be turned high, so NPN will conduct, and this VS positive with respect to this source will come across this GS, and that will turn on our devices. In the if you can follow my arrow here, cursor of this mouse, at the time of this turn on, it will follow like this and will turn on the devices. And also because of this totem pole configuration, we are able to provide the this proper level shifting in the terms of the voltage. Also, these devices may be able to handle that amount of the current. These voltage will be able to provide that amount of current in order to drive this voltage, and these devices will be also be able to handle that amount of the current. So this was able to like provide the proper level shifting at the time of turn on. And what happens during the turn off, as soon as this pulse will go to the low, this will drive this top devices into the off state and will turn on this bottom state. At the time, what will happen during the turn off, this VS minus voltage will get applied to this gate with respect to this source. Both of these voltages, VS positive and VS negative, are with respect to this source. So during the turn off, if you can follow the cursor of this mouse, we'll have this path, and this VS minus will get applied across this gate, and which will cause this device to turn off. So because of this totem pole configuration, we are able to provide the proper level shifting whatever is needed. Like if we have wanted to have during the turn off, turn on positive, we want to have a positive plus 15 volts, and during the turn off we want to have a minus 5 volt. We can have this VS positive plus 15 and VS minus with as minus 5 volts. So we'll be having a, because of this totem pole configuration, we will be able to have a proper level shifting required to drive a particular device. And also what we had seen is both of these voltages are with respect to this source, respect to this source. And what we had seen, if we had having an edge bridge connected to a DC bus, we had saw the high side switch will have the high side switch will have this floating point. floating supply here. Now we had to want to see how will we attain this Vs positive and Vs negative with respect to that floating point, because we had to take into the consideration that floating supply. So one of the ways to tackle this is through this isolated DC-DC converter. So you can have an isolated DC-DC converter, which is usually a flyback, push-pull or forward converter, where we have a primary side where we apply VCC, which is usually a 5 volt, 10 volt, 12 volt. You can see what as per your availability and need, and at the output we get the two voltages like Vs positive and Vs negative with respect to this source. What we do is this source is connected to this as source of these devices. So this both these Vs positive and Vs negative will get applied with respect to this source. Now if we have a plus 15, that will be applied with respect to this, and Vs negative that will be applied across, since this both these sources are connected together, and as such these voltages plus 15 and minus 5 will be this will take into the consideration of the floating point supply. Supply, but there should the other requirement of this isolated DC-DC converter should be like it should have a low ripple in terms of this. Let us say we have this we apply some input, and at the output of this we are able to get the voltage minus 5 and 15, and these voltages should not fluctuate, otherwise our device can go from one region to another. We don't want that thing. If let us say our gate voltage decreases from let us say 15 to let us say 10 volts or something, then maybe our device can go from ohmic region to an active region, and we saw in the active region we had the more losses in the active region. So it should have a our isolated DC-DC supply should have very minimal ripple in the voltage. Also these isolated DC-DC converters should have the isolation raters rated for this, because now the source it will be connected to this source, and if this isolated DC-DC supplies are not rated for this voltage whatever will come here VDC, so this can get damaged, because they should be able to handle that amount of the voltage. These were some of the requirements. This was the some one of way how we could tackle this floating supply at the high side of the high side switch, and this may not be required on the bottom side switch, because we don't have a floating point there, but usually we provide this isolated DC-DC supply for the both of the switches. And there are some other ways to do these things, like the by bootstrap method. That is a cheaper way to do it, economical or a cheaper way to do it, that you will subsequently see in the further lectures how to do that. So some other specifications of these gate drivers will be for these gate drivers, if we have an optocoupler based gate driver, if we are giving a pulse from the controller to the gate driver here, but there will be some propagation delay. After that it will take some time from the controller to the pulse to the gate driver to reach the gate driver, and there will be some propagation delay that will be here. After time it will take some time to rise this voltages from 0 to a particular level at the gate driver in order to drive the circuit. That is the rise time. After that only our switches will turn on. In similar fashion, at the turn off time as well, we'll be having some delay. So we have to take account in these delays, because if we don't take into the account these delays, if we give the pulses to the bottom devices at the time the top device is still in the on state because of this delay, then we can have a short circuit. We have to take that thing in account. So you can see these parameters are provided in the data sheet, like turn on delay time and turn off delay time, and we choose a deadband properly in order to accommodate these delay times, so that our in one leg of one leg, that top device and bottom device are not turned on at the same time. So the other thing is here, like we have uh, we have this optocoupler based. What we saw is here, these are isolated, but you can see nothing is like properly isolated. We may still have some parasitic capacitance because of the dielectric between these two sides. So if we have any dV by dt here on the this side of the driving on the device side, that can have like caused, we have some leakage capacitive current here through this parasitic, and which may have the noise, and which can sometime like falsely turn on this device and so on and so forth. The other thing is like we should have the you should see the common look for other thing is like common mode transient immunity, CMTI. Like if you can see, we had these, if you can see these H bridge, we have the at the high side switches, what we saw is we had a floating point supply where the voltage is varying from like VDC minus to VDC plus. So what is happening because of this change in the voltage here from one value to another, there will be a, and it may take some time to change, the voltage may not change instantly, and it may take some time to change from one level to another as we turn on and turn off these devices. What will be happen, there will be some dVdt that will come across here, uh, which may cause some noise issues and EMI issues in the gate driver. So we have to see there is some rating provided in the gate driver ICs as well, so that should be sufficient enough in order to so that the dV by dt of the devices should not affect our gate driver, so that our gate drivers may not get falsely triggered and so on and so forth. This is usually measured in like kilovolt per microsecond or kilovolt per nanosecond, and it is given in the data sheets. So this was about the something that has been, that was about the optocoupler based, and other thing was discussed is DSAT protection, that we shall cover in the next things, and there will be some other things associated with the gate driver that will be discussed in the subsequent classes, and we shall take up those in the next week. And yeah, that was it what had been taught in this week. Now we shall move to the problem solving sessions. Like we shall take a break for like 1-2 minutes, and we shall go to this problem solving. This is the first problem. In the meanwhile, like kindly think over it, what can be the answer to this question. So let us get back after some time. So this is the first question: which of these functions as the Miller capacitance is the MOSFETs? A is gate to drain, gate to source capacitance. B is gate to drain capacitance. C is drain to source capacitance. Any of you? So we shall see what is done. So if you can see here, we have to see about, like, as soon as we give some VG voltage, what we had seen at the time of the gate process, gate source, gate drives, this VGS will be provided by this gate driver. As soon as we will give this with VG, as initially, like, this VGS voltage will be 0, and whole this VG will be applied across this RG, and our current will start to flow, and CGS will get charged, and CGS will get charged to a point, to a Miller plateau. After that, what happens is, like, this voltage remains at a constant level, and what happens, this since this voltage is constant, this IG will be constant, and this IG will flow through this CGD, and causing this CGD to discharge, and thereby turning on this CGD to discharge, and CDS as well, and to turn on this devices. So we can see during this Miller region, this CGD capacitance, gate to drain capacitance is taken in the picture, so that this is the answer. Which of these functions is a Miller capacitor? It is the gate to drain capacitors, as we had seen here. At the time of the Miller, the CGD will discharge and turning on this device. Now coming to the second question. A MOSFET is in dash region when the gate to source voltage is less than the threshold voltage. Like, the three options are there: cutoff region, ohmic region, and active region. So most of you, I think, are correct here. Is, you can see, we have, like, we had taught about the MOSFET is, we have the three regions, like sorry, this is not forward break, this is a cutoff region, we have active region and ohmic region. So whenever this gate source voltage is less than the threshold voltage, we are in this forward blocking or cutoff region. So till that, if this VGS is below the threshold, what happens is this device is not in the conduction. But as soon as we increase this VGS voltage beyond this threshold voltage, our device goes into the conduction. You can see, as soon as we increase the voltage, VGS voltage, it moves from the cutoff region to the active region first, where we have the constant current. But as soon as we increase this VGS, then after some point, like, we will move from active region to the ohmic region, where we want our devices to operate, because in the ohmic region our current can rise to very high values, and also at that time VDS will be very low, so the loss associated will be very less. So we want our devices to operate in this ohmic region. So the answer to this question is, whenever this gate source voltage is less than the threshold voltage, our device is in the cutoff region. So this is the answer to this question, cutoff region. Now it comes to the third question. An IGBT enters into dash region when the gate to source voltage reaches the threshold voltage. Can anybody? Cutoff region, ohmic region, and active region. So here you can see we have, like, three regions. Sorry, it was here, it's not ohmic region, it is saturation region. So we have the three regions for the IGBT, as we saw in the characteristics. We have the forward blocking region or cutoff region. Forward block is also known as the cutoff region. Then we have an active region and saturation region. So what happens? We are applying a VG voltage, gate to we are applying the gate voltage, but as soon as this gate voltage increases, before as soon as like this gate voltage increase, first we are in the cutoff region, but as soon as this gate voltage reaches the threshold voltage, what happens is our devices turns into the conduction. First it moves from the cutoff to the active region, but if we go on increasing our gate voltage to a particular point, that it will move from an active region to the saturation region, as we had seen the characteristics where, and in this saturation region where is the region where we want to operate our device. So as soon as like our gate source voltage reaches the threshold voltage, it is like the device goes into the active region. It is C answer is the correct answer for this. After that, if we further increase our gate voltage, then we shall move from active region to the saturation region. A floating supply is required for dash gate driver in one leg of an H bridge. Low side, high side, or both? I think this we had extensively discussed. I think all of you should be able to answer this question. Can anybody guess? Anybody? Nobody? Okay, at least somebody I think was listening and had gone through the lectures. So we had discussed, if we have one leg of an H bridge, uh, we have the two devices, top device and the bottom device. So option A is not a correct option. Just I'll go through the explanation and you can see. So we have the two devices here, as I had previously reiterated, like this top devices are called high side switch and this is called the low side switch. Why is called high side? Because it is connected to the positive rail and this is connected to the negative rail. And if you can see, whenever these devices are turned on and turned off, the voltage at this point is like will vary from 0 to VDC. A point with respect to this, when this device is turned on, this will be equal to VDC, and when this device is turned off, it will be when this device will be turned off and this device will be turned on, it will be equal to 0. So it will vary from 0 to VDC, and we know we have to apply, and our controller, in order to turn on these devices, will apply the gate pulses with respect to this emitter. So we have this collector, gate and emitter, so all the gate voltages will be applied with respect to the emitter. So the voltage that is being supplied by the controller has to be given with respect to this emitter for the both device. If we have the if we see for the bottom devices, the emitter voltage will be at a constant level because it's connected to this negative rail and it won't change. However, for the top side device or high side devices, this voltage will change from voltage changes from this emitter voltage changes from 0 to VDC and so on and so forth. So the gate voltage will be applied with respect to this point A, and since this point A is like a floating supply, it has like value 0 and VDC and it is constantly changing, so we have to apply our gate with respect to this voltage. Sometimes like we have to apply with respect to 0 volt, and sometimes we have to apply that a particular voltage with respect to this VDC. So in order to have this the floating volt supply, so this thing is required for the high side switch, as has been discussed here. As I told you, for this high side switch, we need to take into the consideration is this floating volt supply. So I hope like this is clear to everyone. If there is any doubt, like you can ask. So a floating supply is required for the high side gate driver in one leg of an H bridge. Question number 5. Which of the following is or are true while a MOSFET or IGBT is turning on during the Miller period? So we know the MOSFET turns on during the Miller period what happens at during that time. So first it is like there can be multiple like true. For this we have gate to source voltage becomes constant, gate current is constant, drain current rises, gate to drain capacitor discharges from the blocking voltage to on state voltage drop. So now we shall go through these things. We shall see what happens during the turning on of the device during the Miller period. So we know before this Miller period, like our devices is turned off. Now as soon as like our gate source charge reaches to this Miller plateau, what happens after that, ID current when reaches, it starts to flow, and what happens is now these whatever the voltage that is being blocked by this capacitor has to start blocking voltage start to decrease. So that happens during this Miller time or Miller plateau. So what will happen after that? IG was initially charging this VGS. After this VGS reaches to the Miller plateau, this IG will flow through CGD, causing it to discharge and thereby turning on these devices. So you can see gate to source voltage becomes constant. So you can see first one is correct, because after this at this Miller plateau you can see VGS becomes constant. So first option is correct. Now we'll go to the second one. Gate current is constant. So when this VGS is constant, we know this VG is constant. So both of these voltages are constant. So the effective voltage that will be applied across this RG will cause a constant current to flow. That IG will gate current will be a constant. That is what you will see here. As you had seen initially, like our VGS was getting increased, and effectively like VGS was increasing. This was constant. This was causing our IG to decrease. But as soon as this VGS will become constant, and VG is already a constant, that is during this Miller plateau, this IG will be constant. So option second is also true. Now we'll see the C, drain current rises. If you can see the Miller plateau, that drain current is already constant, because drain current rises before the Miller plateau. During this rise time, it had already risen to its peak value and come back to this constant value, and this thing doesn't happen in this. So option C is not the correct option. Now we'll see option D, gate to drain capacitor discharge from the blocking voltage to on state voltage drop. So that is what I had discussed is after this IG will cause this VGD to discharge, and which will in turn turn on this device. So option D is as well correct. So the fifth will have the option 1, A, B and D will is correct are correct. Now coming to the sixth question. In a gate drive circuit, the RMS value of the gate current is dash, peak value of the gate current, equal to much higher than, much lower than and slightly lower than. So anybody? Much lower than. Yeah. So if you can see here, during the turn on, if you can see here, this turn on and turn on time is very small, and you can assume like during the turn on what happens is like this current IG current goes to some peak value and then it comes back. As soon as like our devices turn on, it goes back to zero. But if you can see the current when we apply the VG, and for the portion it is turned on, this IG current is very small portion of the total time our device will be turned on. It will be, let us, if you are switching at 100 kilohertz frequency, that is at around like 10 micro I think, and usually this turn on and turn off time is usually in the nanoseconds. So it is very a small fraction of this. And if you can see, if it will assume as a peaky current, it will be have some peak value and will come back to the zero at turn on and turn off times. And usually if you can see the RMS value of this, if you can calculate, by looking at it itself, you can see it is much lower than the peak of the current, because for the most of the time the current is zero, and it is like a peak value for a small fraction of the time. As such, like what will be the correct option is, like for this sixth is, it will be much lower than the RMS value of the gate current will be much lower than the peak value of the gate current. Question number 7. A totem pole is a combination of an NPN and dash type of transistors. A NPN, PNP, or NC is PN junction. Anybody? So we had seen totem pole in detail. Nobody? So here it is. You can see we had seen the totem pole configuration where we had an optocoupler based this gate driver, and it was not able to usually have the voltage and current level properly in order to drive the device. So we had this control signals from the controller which is trying to drive the devices, but in order to properly have the voltage and current levels, what we have is the combination of an NPN and PNP transistors that we call as a totem pole. So whenever this control signal is high, the LED device causes the diode on the secondary side to turn high, which will in fact, because these are connected to the common bases, it will cause the top devices to turn on, which will have. And also what we know is these both Vs positive and Vs negative are with respect to this source, and this Vs positive is usually like a plus 15, and this minus will be minus 5 in order to properly drive, which is the proper requirement in some of the switches to drive these switches, and it will come across this will be like gate voltage that will be applied across this gate source terminal. And during the turn off time, this PNP will be turned on, and the path will be for the turn off will be this way to turn off this device. So a totem pole is a combination of an NPN and a PNP type of transistors. So part B is correct. Now question number 8. From MOSFET, this is the part number given, so we have to see the data sheet of it. So what is the gate resistor RG used by the manufacturer to measure the turn on and turn off times? So you have to do nothing, just search this part number, download the data sheet, and look for the RG value that has been provided by this manufacturer. So if you can look at this, like this is the snap of the data sheet. So if you can look here, we have the turn on delay time, rise time, turn off time, fall time, that are typical values are given, but the conditions here are given, and the calculation of these values are at certain conditions, like VDD is 50, ID is 16 amps. Here RG is given, that is given for the test conditions, it is 5.1 ohm. That is what is being asked from this question. So the answer to this question is RG will be equal to 5.1 ohm. You just have to do nothing, just download the data sheet and look for this RG value, because it's asking what is the RG value being used by this manufacturer. In a similar fashion, for the MOSFET, like the part number is given, data sheet, what is the maximum value of the total gate charge? You have to see what is the maximum value of the total gate charge that is given in the data sheet. In a similar fashion, you will download the data sheet and go through the data sheet and see what is the value that is given. If you can see here, the total gate charge is given as 971 nanocoulombs, and the conditions here is also given at what conditions it is being measured. ID 16 amps, VDS is 80 volt, and VGS is 10 volts. And this has like also what is given is gate to source charge, and gate to drain Miller charge is also given here. So you can also like see from the graphs here as well. You can see this portion, initial portion is from gate to source charge, then it is like Miller, then again it is like gate to source charge. So for different VDS values we have different curves, because at higher VDS we have the higher charge. So if you can like for a particular, if you can see the test condition 80, if you can see at the 80 it is around like 70, I think it touches the 70 line, and you can see the exact value of it is like 71 here. So you don't if you want at certain other DS values like 50 or 20, you can calculate from the graphs as well, but here it is given for these conditions, and it is the 71 nanocoulombs, and here QG is 71 nanocoulombs. You just only have to write 71 because nanocoulombs is also already written. Just write 71. That is the answer to this question. Also, another question is MOSFET. This is given using the same value of RG as used by the manufacturer to measure the turn on curve. Calculate the IG peak, and VG is given as the 15 volts. So this is the RG value that is given by the manufacturer. So what RG value is 5.1. What we have to calculate is the turn on peak of the current. We saw, if you can go here to the previous, we saw this peak current will be equal to, initially like that VG voltage will be applied, and before that, if you can see here, before that VGS voltage will be equal to 0. Since we can have a negative voltage as well, but since it has not been given here that any negative voltage we had at have at that during the off state, so what will we assume as it is 0 during the off time. So what is the VGA? Initially the voltage that will be applied across the RG, because VGS is initially like voltage is 0, so the peak current will be at that moment. So the voltage, it will be 15, and we will divide that by RG, it will be equal to 0.94 amps. So that will be the answer to this question. Now the other question is like from the MOSFET, this is given if IG peak needs to be limited. Now what we want to do is we want to limit the IG peak to be 2 amps. What should be the value of the RG? Initially the RG value was given here in the data sheet. We had to take that RG value and calculate the peak of this current. What will be the peak amount of current that will flow? Now that was coming out to be 2.94. Now we want to limit this current to 2 amps. So we need to see what will be the resistance that we have to put during the turn on time in order to limit this current. So now we have is RG will be now given by, now we know the we know the I peak, that is to be VG is given, it is 15 volt as previous. Now IG peak we want to limit by limit to 2 amps. So from that we can, using this Ohm's law, we can calculate this RG will come out to be equal to 7.5 ohms. So if you know like what is being asked, like these are very simple questions here also given in the problem sets, so you should be able to like able to solve these questions. So these were the questions that we had to discuss for today. I hope everyone like understood how to like solve this question. Take one question at a time, how to know what is the what is being asked in the question, and how to go about these questions, and so on and so forth. That is it from my side today. And if anybody has questions that he and she can ask. And one of your student had like mailed about the PDF. So if you can go through, yeah, about the PPT, I shall share it. If you can go to the course page, there is one tab towards the left of it, provided about the problem solving session, there is a like Excel sheet that is being shared with you, and in that Excel sheet there will be a Google Drive link where I'll upload this PDF, as well as this video will be uploaded, the link to this video. Because so you go to that page, there is one tab. So if the gate voltage, one of the if the gate voltage is not given, so the question is, just a minute. Usually the gate voltage is provided, the range will be given where we want to like turn on this device. So if the for the negative is not given, like what should be applied, you just assume it to be 0 at that moment of the time. But usually in order to turn on a particular device, the nominal gate voltage will be given. What is the amount of the voltage that needs to be given in order to turn on this device will be provided by the manufacturer. So this will be shared in the NPTEL. If it is not so, you can mail me. I have shared my email ID. You can mail me. Like I shall share this link to this PDF as well as this video with you. So that is it from my side. If anybody has question, any other question, you can he or she can ask. Or if there are no questions, then we can, I think, conclude today's session. Thank you, everyone. So how to calculate the minimum power rating? I think this is the question that is being answered to the in this what should I say, for the problem solving session. I can't tell you how to like exactly do that, but we know that what is the minimum. We had seen the losses power in the gate driver. I had shown this equation with you. So you need to calculate this P, you have to calculate this P gate, and as well as this IGRMS and RG will be given. So Q will be given, VG will be given, you will be knowing the switching frequency. You just have to calculate this. So you go through this and go through this question, that this is the problem solving session. We are not allowed to discuss about that thing, because this question is in the problem solving that has been shared with you. Any other question? Like as soon as the time from this will be ended, if you are not able to solve it, then we can discuss it. So I gave you a hint, like you can go about that. Any other questions? So if there are not any other questions, then I think we can conclude for today. Thank you everyone for joining.